In November 2025, a gravitational wave detector caught a chirp, the signature ripple of two objects spiraling together and merging. Nothing unusual about that. LIGO's logged hundreds of these. Except when scientists ran the numbers on this one, they got a mass for the lighter object of less than 1 solar mass, a black hole lighter than the sun. Every model we have for how stars die says that shouldn't be possible. If that's not possible, did the detector mess up? Or did we just catch something nobody has ever seen before? We're going to keep a ledger through this video. Evidence for, evidence against, and update it as we go. Mark down your first entry because it's about to get less certain than it looks. Here's what I'm actually looking at. A gravitational wave that might be the first primordial black hole ever caught. Or it might be nothing at all. The evidence, it goes both ways. Here's how this normally works. LIGO and its partner detectors, Virgo in Italy, KAGRA in Japan, run as a single network called LVK, and they listen for ripples in space-time thrown off when two extremely dense objects spiral into each other and merge. Black holes, neutron stars, and sometimes a black hole eating a neutron star. Almost a decade of listening has logged hundreds of these mergers, and nearly all of them fit a pattern. Black holes that used to be stars, weighing in at several solar masses and up. That's what a black hole is supposed to weigh, because that's the physics of how one is born. A massive star runs out of fuel, its core collapses, and only cores above a certain mass can crush themselves down into a black hole in the first place. Below that line, you get a neutron star, and even lower than that, you're going to get a white dwarf, not a black hole. So on November 12th, 2025, when an automated LVK alert flagged a new merger cataloged as S2511112 cm, the number came back wrong. Now, here's what the detectors actually measure, because this matters later. Not two separate masses, but a single combined figure called the chirp mass, which for this event landed somewhere between 1/10 and just under 9/10 of a solar mass. From that, the pipeline put better than 99% odds on at least one of these two objects being lighter than the sun. That's not a small discrepancy. It's a whole class of black hole that stellar collapse can't build. And it would be tiny. At that mass, the black hole's event horizon is somewhere between about 0.5 kilometer and 5 kilometers across. Small enough that the entire object would fit inside a city easily, with the mass of a star packed into it. The signal traced back to a galaxy roughly 300 million light years away, and then telescopes all over the world swung around to look at that patch of sky. But they found nothing. No flash, no afterglow, no counterpart of any kind. Mark that down because we're coming back to it. No light, no explanation, just a chirp that shouldn't exist. So how do you tell the difference between we found a genuinely new kind of black hole and our detector hiccuped and it looked like one? You can't just eyeball a gravitational wave chirp on a screen. The real signal is a slight wobble buried in a wall of instrumental noise. And LIGO's mirrors are sensitive enough that a passing truck, a distant earthquake, even the quantum jitter of light itself can produce a blip that looks like something. So instead, LVK scientists ask a more precise question. Across years of pure noise with no real signal in it, how often would a wobble shaped exactly like this happen by pure chance? That number is called the false alarm rate. When the automated pipeline first flagged S2511112 cm, the estimate was that a noise fluke this convincing should turn up about once every 6 years. Then, a specialized search built specifically to hunt for low-mass signals like this one reanalyzed the same stretch of data and tightened that number, roughly once every 4 years. Now, here's the context that number needs. When LIGO announced its first confirmed detection back in 2015, the false alarm rate on that signal was better than 1 in 200,000 years. That's the standard this field holds itself to, and this one is sitting at 1 in 4. That's not LVK being cagey by calling it a candidate. Claiming a whole new category of black hole on a fluke would be a far bigger mistake than staying quiet on a real one. So mark that down in the against column and mark it firmly. But then there's that empty patch of sky, and here's the part that sounds backwards until you sit with it. If the primordial explanation is right, and what merged were two ancient black holes with no stellar material anywhere near them, there was never supposed to be light. No debris, no kilonova, nothing to catch. The absence of an afterglow isn't evidence against that explanation. It's exactly what that explanation predicts. Mark that one down on the for side. Here's why scientists care enough to argue about this. If S2511112cm is real, and at least one of those objects really is under a solar mass, it can't be a scaled down version of anything we already understand. No star, however small, collapses into something that light. That's a record worth quantifying, not just asserting. The lightest object anyone has ever seriously called a black hole is the mystery companion in GW 190814, detected in 2019. About 2.6 solar masses, and even that one is still contested because it could just as easily be the heaviest neutron star ever found. Even the top of this new object's range, under 9/10 of a solar mass, is only a third of that. At the bottom of the range, 1/10 of a solar mass, it's roughly 26 times lighter. There's only one mechanism anyone has seriously proposed for building an object that small. It didn't come from a dying star at all. It formed in the first fraction of a second after the Big Bang, when the universe was dense enough that pockets of it could collapse straight into black holes with no star required. Physicists call these primordial black holes, a theoretical idea dating back to the early 1970s. And one of the leading proposed answers to the biggest open question in cosmology. What is dark matter? The invisible substance that makes up around 85% of all the matter in the universe. Nobody has ever confirmed a primordial black hole. Not one, anywhere, ever. If this signal holds up under more scrutiny, it wouldn't just be a strange gravitational wave. It would be the first direct evidence that primordial black holes exist at all. And depending on how many are out there, they could account for a meaningful slice of dark matter, or, under the most optimistic estimates in this paper, all of it. So, what would actually settle this? Not one paper's statistics. What would settle it is exactly what settled every other gravitational wave mystery: more detections. The team behind this analysis modeled how many subsolar mergers a real dark matter relevant population of primordial black holes should produce, and how many LVK should be catching given how long it's been listening. And this one candidate sits roughly in line with what the population predicts. It's not proof, it's consistent. If they're right, the current detectors running at their planned upgraded sensitivity should start catching more of these. And a handful of events at 1 in 4 years each starts adding up to something no coin flip explains. And 2 next generation instruments are built for exactly this hunt. Cosmic Explorer, in the design phase in the US, and aiming for roughly 10 times LIGO's sensitivity. And then there's also LISA, the space-based detector the European Space Agency plans to launch in 2035, designed to catch gravitational waves from the earliest moments after the Big Bang, the actual era these objects, if they're real, were born in. Which brings us back to that empty patch of sky from the opening. No light, no afterglow, nothing to see. For most stories in astronomy, that's a dead end. Here, it's the prediction working exactly as advertised. So, final tally here. More marks in the for column than the against, but nowhere near enough to call it either way. Mark that down as unfinished. because right now it genuinely is. The paper's linked below if you want to dig into the statistics yourself, and I'd recommend it. An honest, we don't know yet, is rarer in this field than you'd actually think. If LVK catches a second subsolar signal, I'll be back to update this ledger, so subscribe if you want to see how this one resolves. Until then, you've been watching Cappelluti, and here's one for the comments. If you had to bet right now, do you think this was a real signal or just detector noise?